Welcome to a new test and teardown video. Well, I'm sorry, this can't be a test video because they're both dead, so that's just real bad. This is a Velleman PC scope and a PC function generator. I guess it's like 20 years old, this set. And it was actually quite expensive back then. The PC scope here is called PCS500. And it's a 50 megahertz 8-bit 2-channel sampling oscilloscope. This 1 giga samples is absolutely not true in any way. There's a 50 megahertz clock in here, and it's a single cycle AD converter, so it's of course only 50 megahertz. This is just what is the equivalent sampling speed if it was a I don't know, an old type of AD converter or something like that, right? And the function generator is called K8016, 0.01 hertz to 1 megahertz. And again, it's 20 years old technology, using parallel port and using PC software and PCs running Windows 95, 98 and something like that. Windows XP isn't even mentioned in the manuals, so that wasn't invented yet. So if to find software, you can actually find the software on Velleman web page, and you could probably also find an old computer and perform an old installation of some old operating systems and get this up and running and all that kind of stuff. But I would really love to repeat my statement from earlier videos. Please never ever buy products like this that requires PCs and PC software and stuff like this, because this is of course going to get obsolete and it will be transformed into pure trash, and all your money will be wasted after 10-20 years. What you should buy is a real stand-alone scope, any type, any brand, whatever model. It will still work after 10-20 years, no matter what kind of software it contained, because it is self-contained. That's what I'm saying. I got like 50 years old scopes and they still work. Yeah, so I'm just super angry about people buying shit like this, but that's another thing. Yeah, they are, as I said, defect, so we can just have a nice view of how this is all designed. The hardware design here is actually quite impressive, and it is really well done, by the way. The first thing that you see here is obviously inside the case. You see this red paint. It's not just red paint for a reason. It is actually 0 ohms, super conductive, almost paint. So this is for shielding, because of course you can't have any kind of fast electronics, super sensitive stuff like this in a plastic case. So this is a way to convert this case into a metal case. It will at least act as a metal case and still look really nice and sexy because of all the nice and fancy shapes and all that kind of stuff. But it is really going to shield just like a metal case would do. They even got this nice spring for ground here, and obviously the PCB is screwed into this case, and there's a good contact with the bottom part as well. And there are a few hints about this being defect. Well, of course, I found this in a trash can. That is one, and the wires were cut into pieces. So that is definitely somebody was angry about this crap and didn't want anybody else to repeat their misery. But what you can see here is the two black wires for channel 2. Look at that. And let's compare with channel 1. You see what I'm saying? Those two wires, they're flipped. This is of course not correct. The signal here is not ground, right? And the ground is of course not signal, so yeah. This is a clear evidence somebody was in here and screwing around and didn't assemble it correctly, and of course they didn't know, because they didn't manage to get this up and running again, because it's a defect. And I'm not going to spend a million hours figuring out why this is defect, because there's no use whatsoever for such a crappy product like this anyway. Who wants to use an old Windows 98 machine to capture some really low speed, low resolution scope pictures? That is absolutely as useless as you can imagine. But we can enjoy the design here. All the input circuits, attenuation, gain, AC/DC, all that kind of stuff is obviously done by relays. And look at the grounding. There is a nice path here, and that is of course they want to avoid ground loops and noise loops from all the digital stuff to get into the analog section and gain stages. Look, the 280 converters, so they're right here. Yeah, I'm trying to get this sharp. So the 80 converters, ADS830E, they are from 98. So that's 24 years old today. That converter is an 8-bit converter running at 60 megahertz maximum. In this unit it's running 50 megahertz maximum. Like you see here, let me see if I can show you guys this. The 280 converters, they go into, I think this is, yeah, signal conditioning or line driving for fast SRAM. And then we got digital interface, all the other parts here. That's actually digital interface to read out the content of memory, and obviously to set up the relays and handle the timing, the clock and the counting and all that kind of stuff for handling SRAM and triggering. And then it's just going to transfer this nice and slowly via optocouplers to your PC's parallel port. And there's a single 12-volt input, and there's actually I found a schematic showing you how they're generating a negative supply as well. Let me see if I can put this in here so we can see how we got negative supply and also regulators for all the analog and filtration for all that supply stuff. So that is quite nicely done. I don't know what you think about this fuse. I think this is not an original fuse. Somebody has been poking around here a little bit. So yeah, I don't think there is anything useful other than the case is clearly something you could reuse for other funny projects. It's super easy to take up the front and the rear plates here and just mill some new ones, or you can even just put in a PCB and put in your own PCBs and screw that into that case. It's absolutely reusable case. So I really would like to look a little bit on the signal generator as well, because I believe this one got the original fuse, by the way. That is how it's supposed to look like. And the signal generator works a little bit like the scope, but not quite. Again, there is a parallel interface. Here is a through interface, and that means you can have both of these devices connected to your PC using only one parallel port, obviously. And here is SRAM. So what you do is you upload the sine wave or whatever kind of wave you want to generate, and then this wave is kind of just played back using the electronics here. I think this is where we'll find the DA conversion, but I am actually a little bit confused about how this is made, because this does not look like an R2R kind of a network, but I see some line driving done here, and that is counters, isn't it? And then we got some op amps and stuff like that. Relay for probably the output, most likely some drivers. What I think is a little bit funny is this chip, because that's an analog to digital converter, 8-bit. So what the heck is that doing here? This is supposed to be output. We only got outputs. So what's that doing? I haven't figured that out yet. So I'm going to go and see if I can find some schematics, and maybe I can figure out what is that doing. What is the idea? Drift? Level? Oh, I don't know. What is this compensating? What are they reading back? And what's that one doing? This is just a regular, yeah, okay, this is just a 5-volt regulator. And up here is transistor. I mean, not a lot of nothing here. But it's beautiful PCB layout. There's another. Okay, this is 8016. It says also 8016 in here, but it's like here's P and here's K, whatever that means. Here is the schematic of the power supply and the input on off logic and the oscillator used for the negative supply. And then there is of course a nice linear regulator to make a nice clean minus 5 volt for the analog stuff. So yeah, that's a lot of components to make a negative supply, but hey, that's how it's done. Let's look at the input channel 1 analog input, and the first relay is of course the AC-DC relay, and then we go to some attenuators, and at the bottom here a grounding relay, and then we see some field effect transistors, so we can have a very high input impedance, and then we go to some op amps, and that's of course a very fast op amp that provides all the high speed gain, and again we see some relays used to select different gain settings, and then a low impedance driver to the op amp, to the AD converter. In this case, we can see the 80 converter is running off internal references. It is powered off a digital and an analog 5-volt supply, and we can see we got two different grounds, one on the left side and one on the right side. And this is very important if we look at the PCB layout. Let's look a little bit closer at the PCB layout. I don't know if you can see this really clearly, but this is a 4-layer PCB, and what I want you to look at is this gap in the ground. It goes all the way like that, right? But we see a lot of tracks going over here. It's kind of all over the place between that ground and that ground. And let's look at the other side of the PCB here. Again, a very, very confusing ground divide. As you can see here, this is the same kind of ground, but we've got all sorts of crossing wires. This is definitely an example about how you should definitely never ever do that. But I don't know. They've been reading a book about how to do ground isolation and all sorts of stuff, and they completely misunderstand the topic, or had a little bit too much alcohol in the break, because this is definitely not how you do it. Let me just be very, very clear with you guys. If you ever want to make something like this, dividing ground can be a good idea, but of course you must have it completely closed onto the 80 converters, so they should have been placed very, very close together, and all the tracks to anything at all should go and pass that same spot, because otherwise there's no return. Oh my god, you cannot have a signal without a ground. That is definitely forbidden. So don't do that at home. It is funny. I'm not done going nuts about this design. I took out the 80 converters because I really hoped we would have a ground connection from one side to another, underneath here at least, but that is not the case. Look at this. Pin 1 is the ground, right? I think you can see it here. And it is still connected to the right side of that chip. There is nothing, there's no return path on high-speed digital to that side. There's no ground from that IC to or from that IC. No return path, just the signals, not even a ground to follow. How bad is that? So that means the return path of any transients needs to follow that one, or it needs to follow those, or follow the power supply lines over here, or it needs to go and follow those, or go down here where there is actually one single ground connection. So that is, your loop is now absolutely uncontrolled, unwanted, all over the place, because they did this a very, very bad way. That was fun. I don't know. I would be very, very embarrassed to do anything like that, but let's enjoy the signal generator K8016 a little bit more in detail, because I was actually able to find a schematic about this one. And it turns out this is actually a kit. You can buy this, or you could obviously buy this in kit form and solder everything yourselves. There's almost 1,000 solder points here. And this is their most advanced kit, or the highest level of advanced. So definitely not a beginner kit. And maybe you could also buy this as a ready-made, because when I look at all the solderings here, it definitely looks like a professional job, like reflow and proper cleaning and everything like this. So I would guess that they also sold this as a ready-made product, but you could of course also buy this as a kit if you are like really advanced. Ha! How cool is that? And yes, I was looking at the wrong data sheet. The TDA8702 is indeed a digital to analog converter, and that is the one that is playing back the content of the SRAM. So this is 32 kilobytes of memory, of waveform memory, and this goes via all those op amps to the output. But there is actually something that is really, really cool I wanted to show you guys. All this. That's analog multiplexers. And here another one. No, that's not true. I'm looking for the other one. The other one is here. So here we go. So that one is the 4051 and the other 4051. So audio goes, the output goes to those VS. They actually act as a programmable low-pass filter. So depending on the output frequency of the waveform you want to make, is it a fast one or a slow one? How detailed is it? How smooth do you want the output to be? You can select different series resistors, and then you can select different capacitors, and that will create a very variable low-pass filter and smooth your output. So that is a very, very good way to do it, in combination with the memory and the 8-bit DA converter and all that kind of stuff. So I'm actually quite impressed to see this great design. The power supply of the signal generator is quite a lot more advanced. All the parts you see here and all the parts you see here, and you even see a little bit more of it here, and again a regulator here. We also got local regulators here and local regulators here. It's actually I better show this on the schematics so you can better see what is going on. So here we are looking at the signal generator power supply. Again, look at the input connector. There's a series transistor you can enable and disable to turn this thing on and off. And then the oscillator is now inverted and driving two sets of transistors in kind of push-pull, and this is of course to generate less power input ripple, and then you rectify this positive and negative to generate a positive 12 volt, negative 12 volt, positive 5, negative 5, and again a 5 volt and a 5 volt analog. So all those voltages are generated inside the signal generator. Here is the schematic for the signal generator output low pass filter. Like I said, you got all those series resistors, and you can select between which one of those you want to use. And then you have another multiplexer where you select the output capacitors. So this makes up a very flexible output filter. And there's actually another really cool thing. If you look up to your top right, the output enable feature also changes the capacitors selected. So when you go in and out of enable disable, you will have a fast discharge of your output filter capacitors. I mean, that is really smart. And here is the signal generator entire digital part of it. As you can see, we've got a lot of digital interface using clock data input, and then like a serial to a parallel kind of way to get all the bits you want to control all sorts of stuff with. We've got some counters you can reset and set, and all those things, and then we can clock the SRAM with the addresses from the counters, and yeah, that is just a super basic stuff. This is just the way it should be made. And in the bottom right, we see the DA converter.